Hello grade 12s, welcome back to another video. So in today's video we will be doing chemical equilibrium. Don't forget to like, comment and subscribe to this channel. Now if you're struggling with mathematics, business studies, physical sciences and economics, Zane Tutors has a WhatsApp class where you get exclusive videos, notes and question papers. So you will be added to a group and that's where you'll be getting assistant. And the nice thing about it is that you can ask a question whenever you don't understand anything in class and it will be explained to you. Okay, now without wasting any more of your time, beautiful people, let's get into this video. So let's look at this. Okay, systems in equilibrium are balanced systems. Okay, for example, let's say if you're running on a treadmill, you are in a constant motion. However, you are not moving forward or backwards. So as fast as you can run forward, the treadmill is moving backwards. The treadmill is going backwards, you are going forward. So you are in equilibrium with the treadmill. So the same energy the treadmill is going forward with is the same energy you're going forward with in order for you to match the backwardness of the treadmill. So that is what we call equilibrium. So with regards to chemical reactions, the product and the reactant are produced at the same rate. So we're going to be looking at the product and the reactant. So they have to be produced at the same rate for them to be in equilibrium. So we will begin by exploring chemical equilibrium in more details and ways of measuring equilibrium, and the factors that affect equilibrium will be covered. So the first thing we have to know is what is chemical equilibrium. So before we go there, let's look at this. With chemical equilibrium, you need to know Le Chantel's principle. You need to know equilibrium constant, which factors affecting Kc and temperature. You need to know factors affecting chemical equilibrium in concentration, pressure, and temperature. And in temperature, you have to know exothermic reactions and endothermic reactions. So that is what you need to know. Let's look at the extract from the examination guideline. So in this section must be read in conjunction with your textbook, but a lot of schools now do not use textbook. So chemical equilibrium and factors affecting equilibrium. So you need to know and explain what is meant by an open and a closed system. So an open system continuously interacts with its environment, while a closed system is isolated from its surroundings. And a reverse reaction. A reaction is reversible when products can be converted back to the reactant. So a reactant is the one that the outcome of a reactant, if you react two chemicals, they produce a product. So when that product can be reverted back into different reactant, we call that a reversible reaction. And then we have chemical equilibrium. It is a dynamic equilibrium when the rate of the forward reaction equals the rate of the reverse reaction. So that is chemical equilibrium, and you need to list the factors that influence the position of an equilibrium, like pressure. Those factors are pressure, concentration, and temperature. And then the equilibrium constant is Kc. List the factors that influence the value of the equilibrium constant Kc. Write down an expression of the equilibrium constant having been given the equation for the reaction, and then perform calculation based on the Kc value, and then explain the significance of high and low values of the equilibrium constant. So the principle of equilibrium principle, you need to state the Le Chatel's principle. When the equilibrium in a closed system is disturbed, the system will reinstate a new equilibrium by favoring the reaction that will oppose their disturbance. So whenever you're trying to disturb an equilibrium, the equilibrium will produce a reaction that opposes the disturbance, so it does not want to be disturbed. And we use the Le Chatel's principle to explain change in equilibrium qualitatively, and then interpret graphs of equilibrium, which is concentration rate, number of moles, mass, volume versus time graph, and explain the use of rate and equilibrium principle in the Haber process and the contact process. So firstly, we have to know what is a chemical equilibrium is a reaction in a chemical equilibrium where the rate of forward reaction equals the rate of reverse reaction. So that is a chemical equilibrium. So chemical equilibrium is the state of reverse reaction where the rate of forward reaction equals the rate of the reverse reaction. That is it. If it's good that you write notes while we're doing this, that the forward reaction is equals to the reverse reaction. So that in its state is what we call chemical equilibrium. Now, the second thing that we're going to look at is the type of systems, okay? We have an open system. So an open system continuously interacts with the environment. So for example, when boiling water using container without a lid, water vapor will escape from the container to the surrounding environment. So that is an open system, okay? Open system continuously interacts with the environment. You have to know that, okay? So there is exchange of energy and matter in an open system. So when the pot is open, the vapor is escaping from the container. It means condensation cannot take place, which is the reverse reaction, okay? So in an open system, there is no condensation, which means there is no reverse reaction, okay? That's what you have to know. And then in a so H2O, it becomes H2O. So in a closed system, so there's no condensation in an open system, guys. So in an open system, there's no reverse reaction, okay? Keep that in mind. Open system, no reverse reaction. And then in a closed system, it is isolated from its surroundings. So is one in which energy can enter or leave, but matter cannot. So it's isolated from its surroundings. It exchanges energy but not matter. So matter is not exchanged in a closed system, but it is exchanged in an open system. Okay, what is matter? Any substance that has mass and can take up space is matter. All right, so in the above system, which is a closed system, reactants and products do not escape from the system because the system is closed, no interaction with its environment. So the reverse reaction will take place in the system. So remember, in a closed system, there is reverse reaction, but in an open system, we do not have a reverse reaction. So with this closed system, only energy can move in and out of the system. Matter cannot be gained by the system nor lost from the system in a closed system, okay? So that is how we will sum up an open and a closed system. Easy busy. Now we're going to look at the reverse reactions and so forth. A reaction is reversible when products can be converted back to the reactant. So you take two elements, react them together, but you're able to separate them as well. You combine them, but you're able to separate them. So which means there's a reverse reaction there, because we can convert, we can take a product back to its natural state, whereby the two things or three things that were mixed to form this product can all be separated back into their original state, okay? So a reverse reaction consists of a forward reaction and a reverse reaction. Reversible reactions reach equilibrium in closed system. So reversible reactions reach equilibrium in a closed system. Note that, okay? Initially, the rate of the forward reaction decreases since the reactant are being used. So initially, the rate of the reverse reaction increases since the products are being formed. Okay? So what this means is that, so this is the forward reaction, this is the reverse reaction. Okay? So when we have, let's say, H2 plus O, and then we are going to have H2O. We combine two hydrogens and one oxygen, and then the outcome, which is the product, will be the H2O. But the reverse of H2O will have two hydrogens and one oxygens. So that is what is meant. by that. So when we form H2O, we have forward when we form water, but when we reverse the water to separate the hydrogen molecules from the oxygen molecules, we have what we call a reaction. So another thing you have to know is that a reversible reaction is a chemical reaction that can proceed in both the forward and the reverse direction. Okay, so in other words, the reactant and the product of the reaction may reverse role. Okay, it might be that the reaction can be a product and the product can be a reaction. Okay, so those two lines here show the reverse reaction. Okay, they show the reversal reaction as well, that this thing can change. You can either go forward or backward. And then we can just take a small example. Let's say for this example we will say this is the forward reaction. That's where we'll say the H2 is a gas plus L2 is also a gas. When we do a forward, we turn this product into a reaction. We have 2HL. Okay, so you need to look whether it's balanced. So this side we have 2 hydrogens, and this side, okay, this one is balanced. This is balanced. You just check, you just do this to check if everything is balanced. Okay. So you will say H2 gas plus L2 at gas, and then for forward reaction we will have 2HL. Now to check if this chemical equation is balanced, you will say the H we have 2 this side, and then the H this side we have 2, so there are 2, and then we'll say the L we have them 2 this side, and then the L, because of this 2, this is a coefficient applies to H and L, so which means we have 2. So what we can say is that this chemical formula, this reaction formula is balanced. Now when we reverse this, we'll say the 2HL will now become H2 gas plus the L2 gas. So that is the reverse reaction. The product is now being reversed. The reaction, sorry, is now being reversed into the product, or the product is now being reversed into a reaction. Remember that chemical equilibrium is a dynamic equilibrium when the rate of forward reaction equals to the rate of reverse reaction. So here we have definition of an open system. This is exactly the way according to the examination guideline, and this is the definition of a closed system, and this is the reverse reaction. So we will look at the change of rate of forward and reverse reaction in a closed system. Although it is not always possible to observe any microscopic changes, this does not mean that the reaction has stopped. So the forward and reverse reaction continue to take place, and so microscopic changes still occur in the system. Okay, this state is called dynamic equilibrium. So this is a definition of dynamic equilibrium. There is a dynamic equilibrium when a reverse reaction there is a dynamic equilibrium in a reverse reaction when the rate of the forward reaction equals the rate of the reverse reaction. So the amount of reactant and the product remain constant. So let's look at these two figures. Okay, though that dotted orange line for the first figure is the forward reaction, and that red one is the reverse reaction. Okay, so in the second figure, that blue one is the reactant and the red one is the product, and then those dotted purple lines, that's where we call the equilibrium. So we're going to look at rate and concentration. So looking at the rate of reaction, which is figure 1, you are going to see that the forward reaction here, it's high or fast, but the reverse one is slow. Okay, it's slow. And then the forward reaction starts high and slow down as it gets to equilibrium. Here is the equilibrium. So the forward reaction starts high and gets slow when it gets close to equilibrium, but the reverse reaction starts low and gets higher when it gets close to equilibrium. That's another thing that you guys have to know with regards to the rate figure. So here they are now both at a constant rate. Okay, they're both, the forward reaction and the reverse reaction are both at a constant rate at equilibrium. So both these graphs have reached dynamic equilibrium at T1, both of them. That's what we can see. And then where the curve flattens, after T1, the rate of forward reaction is equal to the rate of reverse reaction. And after T1, concentration of products and reactants remain constant. Avoid saying the following: forward reaction is equals to the reverse reaction. So say the rate of forward reaction is equal to the rate of reverse reaction. So say rate, or say concentration. If it's a rate graph, figure 1 is the rate graph, 2 is concentration. So rate, the rate of the forward reaction is equal to the rate of the reverse reaction, or the concentration of the product and resultant remain constant thereafter equilibrium. Okay, so avoid saying whatever that has been highlighted. And then factors that influence the position of a chemical equilibrium. So these are the factors that affect factors that influence the position of a chemical equilibrium. There are 3 factors that influence the position of an equilibrium. So equilibrium is affected by temperature, by pressure, and concentration. Okay, let's first look at temperature. So yeah, we have temperature, concentration, and pressure. Those are the 3 factors that influence the position of a chemical equilibrium. So firstly, we look at temperature. Okay, concentration only applies to aqueous solutions and gases. So when we have a chemical reaction, in the brackets there should be an aqueous solution, AQ or G, that only applies, concentration only applies to those ones. Okay, concentration of pure liquids and solids remain constant through the reaction. That is why they do not affect the chemical equilibrium. So concentration of pure liquids does not affect chemical equilibrium. And then pressures and gases. Note that pressure is inversely proportional to volume. So when the volume goes high, the pressure goes down. When the pressure goes down, the volume goes high. So they're in proportion, okay? Inversely proportional. And then we are going to look at Lachantel's principle. So when they say factors that influence position of a chemical equilibrium, you say its temperature, its concentration, and its pressure. Those are the 3. Now with the Lachantel's principle is that when an equilibrium in a closed system, when the equilibrium in a closed system is disturbed, the system will reinstate a new equilibrium by favoring the reaction that will oppose the disturbance. So when you read this statement, is that when the equilibrium in a closed system, so we have an equilibrium, this equilibrium in a closed system is disturbed. So the system will reinstate a new equilibrium. So we have an equilibrium, and this equilibrium that we now have is being disturbed. The whole system will reinstate a new equilibrium, will form a new equilibrium by favoring the reaction that is trying to take place, that will oppose will favor the reaction that will oppose the disturbance. So it does not allow the system will not allow itself to be disturbed. It will rather favor the reactions that will oppose the disturbance that is trying to take place. Okay, so what you have to know again is that if you change the concentration of a reactant, then the position of the equilibrium will shift to counter-attack the change. So let's say you want to change, you have a glass full of Oros, you want to change, you put water in it. A reactant, you want to change the concentration, right, of that reactant. So when the position of the equilibrium, when you were trying to change the concentration of a reactant, the position of the equilibrium will shift to counter-attack that change. So the system will try to attack the change that you are trying to put into the system, okay, while we are still of La Chantel's principle. So if you change the temperature of the reaction, the equilibrium will shift to counter-attack the change. So whenever you change the concentration, the temperature or the pressure of any system of a reaction, the equilibrium will shift to counter-attack that change. Okay, that is the La Chantel's principle. So whenever you're trying to increase temperature, concentration, or pressure, the system will shift to counter-attack that change that you are trying to do. So it's very important you know that. So when you increase concentration of a reaction, the equilibrium will shift in direction of the reaction that uses the reactant, so that the reactant concentration decreases. Let's talk about that. Before we go there, let's look at exothermic reactions and endothermic reactions. So an exothermic reactions are reactions that releases energy. Okay, so energy is released in exothermic reaction, and then endothermic reactions are reactions that absorb energy. So when applying the La Chantel's principle by changing equilibrium conditions, the equilibrium position will shift in such a way to counter-attack or oppose the disturbance, as I have just said. So with the exothermic reaction, the reactants are greater than the products. And then with endothermic reactions, the reactions are smaller than the products. So let's look at temperature number 1. What happens when you are trying to increase the temperature of a reaction? Here is a reaction and you are trying to increase its temperature. That will favor the endothermic reaction, a reaction that decreases the temperature of the system. So when you are trying to increase the temperature, the system will also want to decrease. So you are trying to increase the temperature, the system itself will try to decrease the temperature, and then that's where it will favor endothermic reaction, whereby the product is stronger than the reactant. So you are trying to increase the temperature, but what does the system do? It tries to decrease the temperature of the system. Okay, but when you are trying to, that's when you're trying to increase the temperature. When you are trying to decrease the temperature, it favors exothermic reaction, a reaction that increases the temperature of the system. So when you are trying to decrease the temperature, the system will try to increase. So there is also a vice versa. That's why the La Chantel's principle says, when you're trying to do something to a system, the system will do the reverse of what you're trying to do to it. Okay, so a decrease in temperature, endothermic reaction; increase in temperature, exothermic reaction. You need to know that. And then with regards to concentration, which is only deals with aqueous solutions and gases. When you are increasing the concentration of a reactant or a product, it favors the reaction that uses the substance. Adding a reactant favors the forward reaction. When you are adding a reactant, so when we have a system, a reactant, we're having a reactant or a product, right? And then when you increase the concentration of a reactant or a product, when you add a reactant, it favors the forward reaction. So in a concentration, when you add the forward, let's say we have a reactant. I'm trying to explain this to make sense. We are having a reactant. So in this reactant, you increase the reactant. That favors the forward reaction. When you add more reactant, it will favor the forward reaction. But if you have a product and you're increasing the product, the concentration of the product, it favors the reverse reaction. So whenever you're increasing the concentration of the product, you're going to favor the reverse reaction, and whenever you're increasing the concentration of a reaction, you're going to favor the forward reaction. Okay, now decreasing of concentration favors the reaction that increase the concentration of a substance. So with decreasing the concentration of a reactant or the product, the system is going to favor the reaction that increases the concentration of a substance with regards to concentration. So removing a reactant, here you are decreasing the concentration of a reactant. The reverse reaction will be favored, and then when you are decreasing the concentration of a product, forward reaction will be favored. I hope you understand, guys. I'm trying to make this as easy as possible. And then with regards to pressure is gases, deals with gases. So when you increase pressure or decrease volume, increase pressure or increase decreasing volume, it favors the reaction that forms the smaller amount of gases or side with less gas molecule. So when you're trying to increase pressure, the side it favors the reaction that forms the small amount of gases with the less. So the side that has less amount of gases will be the one that is favored when you increase pressure. But when you decrease pressure, it favors the reaction that forms more amount of gases. So it favors the amount that forms more amount of gases. Okay, note that pressure of gases will not affect the position of equilibrium if there are equal number of moles and gaseous reactions and product. So let's look at this example 1. Hydrogen and iodine are sealed in a 2 centimeter container. The reaction is allowed to reach equilibrium at 700 K according to the following balanced equation. H2 at gases plus L2 at gas. This is the outcome. And then we have the change in H is greater than 0. Okay, so as I have shown you, you have to know that is a hint to this example. So define reverse reaction, and then in the solution we say a reverse reaction is when a product can be converted back to reactant. Okay, and then number 2 is forward reaction endothermic or exothermic? A forward reaction, is it endothermic or exothermic? Is endothermic. So a forward reaction is endothermic. When we're talking about so endothermic reaction are reactions that absorb energy, okay, whereby change in H is greater than 0, and endothermic, we see it by evaporating liquids, melting ice, and decomposition. That is endothermic. Okay, so it's a forward reversal, it's a forward reaction. And then exothermic reaction, chemical reactions that release energy by light or heat. So that's where you see that change in H is less than 0, like burning of a candle, roasting iron, or burning of sugar. It's exothermic reaction. So here we answer according to that thing that we are made. Change in H is greater than 0. So that's how you're going to do it. So the temperature of the system is now increased. So the temperature of the system is now increased. Explain the effect of the increase in temperature on the equilibrium position using La Chantelle's principle. So the temperature is increased. So when the temperature is increased, what's going to happen to the system using the La Chantelle's principle? Here, increase in temperature favors endothermic reaction, as I've shown you above. Forward reaction is endothermic. Forward reaction is favored and the rate of reaction increases. So the concentration of the HLG increases. This is how you're going to answer in your exam. Keywords, very important. Now, when we look at 1.4, it says the temperature of the system is now decreased. When we decrease the temperature, this is how we do it. Decrease in temperature favors exothermic reaction, and then the reverse reaction is exothermic. Yes, the reverse reaction is exothermic. The reverse reaction is favored, and the rate of reaction decreases. So the concentration of decreases while the concentration of H2 and L2 increases. This is how you will answer this question. And then, yeah, we are done with this one. Okay, when we are dealing with change in pressure, these are the steps that you're going to follow. You have to balance the chemical equation. So count the number of gas moles on both sides of the reaction using balanced equation, coefficients of the reactant and product. So determine which reaction has more or less number of gas moles between forward reaction and reverse reaction. So 2A, A is a gas, B is a gas, C is a gas, D is a gas, okay? So here in the forward reaction, we have 2 A's and 1 B, which is 3 moles. And then in the right hand side or the left hand side, we have 2A and 1 B. And then we look at the coefficients, and then in the right hand side we have C is 1 and D is 1. So we have 2 moles and 3 moles. So the forward reaction has 2 moles. Yeah, so about that, the forward reaction has 2 moles. The forward reaction is the outcome. So the outcome of the 2A and 1B is C, 1C and 1D. So that is the outcome, is the forward, okay, reaction. That's how you look at it. And then the reverse reaction is the one that we started with. We have 3 moles of gases. And so you determine if the forward or reverse reaction is favored using La Chantelle's principle. When pressure is increased or decreased, state how the concentration of reactants of product change. So that's how you do it. Let's look at this example. Hydrogen gases react with sulfur powder according to the following balanced equation. So we have two H's and 1 S. So that will be 3 in the left hand side, and then in the right hand side we still have 2 H's and 1 S. So it's balanced. We have 3 moles. State the La Chantelle's principle. It says when equilibrium in a closed system is disturbed, the system will reinstate a new equilibrium by favoring the reaction that will oppose the disturbance. And then we have, is the reaction reversible? Explain your answer. Avoid saying there is a double arrow, but that double arrow states that it is reversible. So you just say yes, the product can be reverted back to reaction. So don't say about double arrow, and do not also say reactant can be converted to product, okay? So product can be reverted back to reactant. That's how you answer. And then 3.3, which reaction has more number of gaseous moles? And then when we go to the answer, is the reverse, the reverse reaction. And then let's look at which reaction has less number of gas moles, and that is the forward reaction. So 3.5 says, how will the increase in pressure affect the amount of... If you are confused how we answer 3.3 and 3.5, we only look at the gaseous moles. The gaseous ones are those ones with they said which reactant has more number of gaseous mole, and then we said the reverse reaction. As you can look that the G has 2, so it's more. There's 2, so that's why. Okay, so but that is with the reverse has more G's, and then the forward reaction has less G's. If you can see, yeah. So that's how we're gonna do it. So 3.5 says, how will the increase in pressure affect the amount of H2S G's? So 3.5 says, hint, number of moles on both sides are equal. So increase in pressure will not affect the chemical equation, but the rate of forward reaction and rate of reverse reaction equally. So no effect. And then, yeah. Now let's look at equilibrium constant. Equilibrium constant is the ratio of the concentration of products to the concentration of reactant at the equilibrium. Okay, so that is the equilibrium constant. Is the equilibrium constant is the ratio of concentration of products. And then Kc value has no units because it is a ratio of concentration. So A, B, C, D represent coefficients of the reaction and product, and are put as exponents in the Kc expression. Always use square brackets to represent concentration of the substance. Do not use other brackets in the Kc expression, but only square brackets. When substituting in the K expression formula, use only round brackets, not square brackets when you are substituting. Note that do not include solid or pure liquid substance in the Kc expression, and reason is that concentration of solids and pure liquids remain constant throughout the reaction. When Kc is equals to 1, meaning the concentration of the reactant are equal to the concentration of the product. When Kc is greater than 1, higher concentration of the product formed than reaction. So this implies that equilibrium position shifts to the right, and then forward reaction is favored and high yield or more product is formed. But when Kc is less than 1, high concentration of the reactant is formed than the product, and this implies that equilibrium position shifts to the left, which reverse reaction is forward, and low yield, less product is formed. So factors affecting equilibrium constant, we have temperature. It is the only factor that changes the value of Kc. Kc is temperature dependent. So a factor affecting Kc is temperature. Note, you must know that the following factors do not affect equilibrium constant at all. So concentration, pressure, and catalyst do not affect equilibrium constant at all. It's only temperature. Okay, so here you're asked to write down the Kc expression of the following equations, chemical equations. So we have 2H and 2Cl gases. So the Kc expression is product over reactant. But how you write it, you don't say product over reactant. You write the product in those brackets. You write HCl. It's 2 HCl. So you write squared at the top. And then for the reactant, you will write them separately. It's 2H and 2Cl. Okay, if it's there, the 2, that 2 on 5.1 in front of HCl is the coefficient. So if there's a coefficient, you write it as an exponent, okay? But if it's at the bottom, like at H2G plus Cl2, you still write them like they were. And then on 5.2, this is how we write the Kc. The product is on top and the reactant is at the bottom. So the coefficient is still an exponent because it applies to the two elements, to the N and to the H. So yeah. So another hint is that remember that solids and pure liquids should not be part of Kc expressions since their concentrations are constant throughout the reaction. So we have solids, S means solids and L means liquid, AQ means aqueous, and then G means gases. So gases and solids are not part of Kc expressions since their concentration are constant throughout the reaction. So we will just take the D. Yeah, this is the only thing that you will substitute. So don't include with constant, don't include solids and liquids. Another thing you should remember from grade 10 is the concentration. That it's over concentration equals to mole. The N stands for mole and the V stands for volume. Okay, and then we're going to look at this example. Yeah, we're almost done. We are almost done with this video. Yeah, don't forget to like, comment and to subscribe. If you're watching this far, it means you're enjoying and you are learning from this video. So don't forget the WhatsApp classes as well. Yeah, so here we have example 6. In the reaction, 5 moles of N2G and 8 moles of N2 gases is introduced in a sealed 50 cm cubed container. The reaction reaches equilibrium at 400 K. At equilibrium, it is found that 2 moles of NH3 gases is present in the container. So we have N2G plus 3H2G. The reverse reaction is 2NH3G plus heat. So calculate the Kc value at this temperature. This is 7 marks. So I'm going to show you the steps you're going to follow. This is the table that you're going to write. We have H, we have N, and we have NH. Okay, so that's what we have as the product. For what reaction? Write it in the third. So that those are the amount things that we have. So you're going to write ratio, initial quality, change formed, quantity at equilibrium, and then equilibrium concentration. So for the ratio, what you're going to write for the ratio is the coefficients. Okay, that's what you are writing for the ratio. You're writing coefficients. So the coefficient of this N2 is 1, there's nothing there. Of this one is 3, which is this 3 here. This 3, where is it not writing? This 3 there, yes, is the coefficient of H, and then this 2 here is the coefficient of NH. So that is exactly what we will write at the ratio. And then initial quantity, we're writing moles. So we are given the moles up here. In this reaction, 5 moles of N2 and 8 moles of H2. So those are the ones that you are going to use to write as initial quantity mole. So it's 5, 8, and this NH is 0. And then we are going to write change in mole or mole used or form. So we are going to use the coefficients that we used, the ratios. So here we have 1 for NH, and then for H2 we have 3, and then for NH3 it's 2. So we write ratios. And then quantity at equilibrium, we say initial quantity minus the ratio. So for N2 it's going to be 5 minus the 1, this 5 minus this 1, and this 8 minus this 3, and this 0 minus this 2. So those will be our quantity at equilibrium. Okay, and then we will now have equilibrium concentration. So concentration equals to mole over volume. So quantity at equilibrium will be our mole. Okay, so we'll do 4 over initial quantity, which is the 5. This will be our quantity, our volume, sorry. Yeah, so those will be our initial quantity, will be our volume, and then that is how we get that will be equilibrium concentration. And here we have done we do product over reaction. So we have substituted it in square brackets. Okay, those elements, you substitute them in the square brackets, but the numbers in a round bracket. So all the answers we got here as equilibrium concentration are the ones that we will substitute there, and then the Kc is 0,2. So this is how you get your 7 marks. So is the reaction endothermic or exothermic? Is an exothermic reaction. And then 6.1.3 says, explain the answer in 6.1.2. Energy is released by the system. And then the temperature of the reaction is decreased to 300 K at equilibrium. State whether the value of Kc will increase or decrease. And here it says that the temperature decrease. So forward reaction is exothermic. A decrease in temperature favors exothermic reaction. Equilibrium position will shift to the right. And for 6.2, when we increase, is that decrease in temperature favors exothermic reaction, forward reaction is exothermic. So that is how you answered that. 6.2.2. I'm going to show you another example. Do it by yourself, and then I'll show you answers. So just pause the video, do the example, and then mark yourself. This is the example. Here you will learn how to get the Kc value. And here's the solution. And here you have to know that initial rate of a reverse of a forward reaction, you have to know the one that starts at 0 and the one that that starts high. Okay. this one, addition of a catalyst at equilibrium. This is the table, and this is the explanation at the bottom. And then the last thing we have to look at is that a catalyst is a substance that speeds up a chemical reaction or lowers the temperature or pressure needed to start one without itself being consumed during the reaction. So that is a catalyst. Thank you very much for watching, guys. Until the next video.